Welcome to the fourth section of Chapter 25 on geometric optics. In this fourth section, we are going to be working with calculations based on spherical mirrors. So where is the image? How big is it? Okay. We're going to begin by reviewing what we saw in the last unit, that concave mirrors can produce three different types of images. They can create real, inverted, and diminished ones when the object is out past the center of curvature. They will produce real, inverted, and enlarged one when the object is between the center and the focal point. And they can produce virtual, upright, and enlarged images when the object is between the center of the mirror and the focal point. And convex mirrors can only produce one type of image. It is always going to be virtual, upright, and diminished. For calculations, we need equations. So first, the mirror equation relates the focal length of the mirror to the object distance and the image distance. So really quick labeling. F is going to be the focal length. Remember, the focal point is the focal length away from the center of the mirror. Object distance is DO. And image distance is DI. The other formula we need is the magnification. There are two ways of calculating the magnification. One is by taking the negative ratio of the image distance to the object distance. And the other one is by taking the ratio of the image height to the object height. So HI is how big is the image. And HO would be how big is the object. If I were trying to image a 4-meter tall tree using a spherical mirror, HO would be 4 meters. Okay. To use these formulas, there are a set of sign conventions that you have to follow. Here are the sign conventions when using these formulas for mirrors. A concave mirror will have a positive focal length and radius. The convex mirror will have a negative focal length and radius. Really quick, remember that the radius of curvature is by definition 2 times the focal length. The object location, DO, will be positive when the object is real, when it is in front of the mirror. You can get virtual objects which would require a negative object location. In order to do that, you have to have multiple optics, so 2 mirrors, a lens and a mirror, something like that. We're not going to be dealing with virtual objects in this class. Images, when they are real, are positive. When they are virtual, they are negative. Image heights and magnifications are positive when the image is upright and negative when they are inverted. Now we're going to do 2 examples. In these examples, we want to determine the values of everything we don't know and also to determine what type of image this mirror is currently producing. Okay, so really quick, for a convex mirror, following what we saw last week, or last unit, I guess, the answer should be that it's virtual, upright, and diminished. So this should be virtual, upright, and diminished in the end. Let's see if that's what we get. Okay. For this example, we have an object distance of 20 centimeters. We have a focal length of -5 centimeters and an object height of 0.5 centimeters. We want to determine the image distance, the magnification, and the image height. We cannot determine the magnification and the image height until we know the image distance, which we find using the formula which relates the focal length to the object and image distances. So 1 over -5 centimeters equals 1 over 20 centimeters plus 1 over di, which means 1 over di equals 1 over negative 5 centimeters minus 1 over 20 centimeters. Really quick, as a reminder, you have to remember your rules for adding and subtracting fractions here. 1/5 plus 1/20th, or subtracted in this case, does not make 1/25th. It will never make 1/25th. First thing you have to do is find a common denominator, which in this case is 1 over 20. So 1/5 becomes negative 4 over 20 because it was negative up above. We then subtract off 1 over 20, which results in negative 5 over 20 centimeters. That is 1 over di. To get di, we got to flip that. So that becomes 20 centimeters divided by negative 5, or in other words, negative 4 centimeters. Okay. First things, notice it's negative. That negative sign immediately tells me this image is virtual, because that's what the sign conventions tells me. Okay. Next, let's find the image magnification. So the image magnification can be found by the negative ratio of the image distance to the object distance. So that's negative 4 centimeters divided by 20 centimeters, which is positive 1/5. There are no units on the magnification. Okay. This tells me a couple of things. First, I see that this is positive. By the sign conventions, that tells me that this is upright. The other thing I see is that the absolute value of m is less than 1, and that tells me that it is diminished. Why did I absolute value? Well, remember, the magnification can sometimes be negative, and what I really want to know is this number bigger than 1 or less than 1? Is it a fraction or not? So now I can see I have a virtual upright diminished image, which is consistent with what we saw from the ray diagrams last unit. Lastly, we use the other definition of the magnification to find the image height. Rearranging, we find that the image height is the magnification times the object height. The magnification in this case is 1/5, and the object height was given as 0.5 centimeters. 1/5 of 0.5 is 0.1 centimeters. I can, off of this answer, pull the same information I got from the magnification. First, I see that HI is positive. That tells me that it is upright. And next, I'm going to compare HO and HI, and I see that HI is less than HO. And again, I've absolute valued because we might have a negative sign in here, and I don't want that to interfere with this judgment. I see HI is 0.1, HO is 0.5 centimeters, which means HI is smaller, therefore this is diminished. For our last example, we're going to do a concave mirror. I see F is 5 centimeters for this example, which means that RC is going to equal 10 centimeters because it is twice the focal length. That tells me that DO is greater than RC. If I again flip back, when DO is greater than RC, my image should be real, inverted, and diminished. So I should expect a real, inverted, diminished image. We're going to proceed through the math exactly as we did on the last slide. So first we're going to find the image distance using the formula that relates the focal length, the object distance, and the image distance. So 1 over 5 centimeters equals 1 over 20 centimeters plus 1 over di, which means 1 over di equals 1 over 5 centimeters minus 1 over 20 centimeters, which is 4 over 20 centimeters minus 1 over 20 centimeters, or 3 over 20 centimeters, is 1 over the image distance. Again, to find the image distance, I've got to invert that, which is 20/3. For those of you who don't like fractions like that, this works out to be 6.67 centimeters. And I lost my decimal place. There it is back. Okay. I see that DI is positive. By the sign conventions, positive image distances result from real images. So this image is real. Now I can find the magnification. So we just found an image distance of 6.67 centimeters. Object distance was 20 centimeters. That gives me a magnification of a negative 1/3 because I have this negative out in front in my formula that just carries through. Okay, so now I see that M is negative. Because M is negative, that tells me I am inverted. And again, the absolute value of M is less than 1. I have a fraction here. That tells me it is diminished. Okay. Lastly, we again need to find the image height, which I'm writing this formula a little bit backwards, but it all comes out in the end. The magnification is the image height divided by the object height. So that tells us that the image height is the magnification times the object height, which is negative 1/3 times 0.5 centimeters, which works out to be negative 0.17 centimeters. As before, I can pull off of HI the same information I was pulling off of M. So I see HI is negative. That again tells me it's inverted. And again, if I compare, ooh, that H did not turn out very well. HI and HO, I see that HI is smaller. Therefore, it is diminished. So the results I got from the calculations agreed with the results I got from the ray diagram analysis and looking at the simulation in the last unit.